Hello, everyone. Good morning and welcome to another TELOPS webinar. My name is Joe Carrock. I am a field applications engineer for TELOPS USA. We are part of Exosense Group. And today I have a presentation for you titled Optimizing High-Speed Thermal Imaging for Energetics Research. And while we get started, I would like to offer up a poll if I can. This is a standard poll we like to run at the start of our webinars. It also gives folks a little bit more time to come in. But this poll will ask, what is your knowledge of infrared imaging technology? This helps us gauge your interest and knowledge level of infrared technology so that we can guide future webinars towards that content level. I would say that this presentation is on the lower or mid-level side in terms of material today. It is more geared towards talking about concepts which you might need to consider and options that are available to you when creating an energetics research imaging plan in the infrared. However, there will be something for everyone. There's certainly at least some new data with our powerful new HDR M700 system, which I think everyone will be interested in. And of course, if any of these topics interest you, I think I'll be a broken record this morning. Please do reach out. We have my emails here. Either of them reach me. They're both to the same account. And we'd be happy to talk to you about anything that you see here today. Okay, so we'll give that poll just a couple more seconds. It looks like it's a pretty good mix across the board. Some folks with less experience, some folks with more experience. I don't see anyone that's checked thermal imaging expert yet, but I think you guys are selling yourselves short. Fair enough. So that's a good mix. We'll stop the poll right there. And with that, we'll just jump right into it. And so first, we'll start with a question. What is required to capture energetic events in the IR? And these are the main topics we'll talk about today. First and foremost, that is speed. Energetic events are complex and rapid with changes on the order of tens of microseconds, sometimes even faster than that. And so high speed, high frame rates are absolutely necessary to be able to capture these events and to retrieve good data from the events on these rapid time scales. If you don't need high speed, or if you need to trade high speed for something like dynamic range, TELOPS also has you covered with cameras like that M700 HDR. And this is often necessary because of the wide temperature gradients, the large temperature deltas, and the thermal profile evolution that is common for energetic events. We will also pass the trade-off between speed and dynamic range and the options available there. Talk a little bit about calibration and emissivity, which is important to understand in terms of your data and your results. You need to understand the difference between radiometric temperature and absolute temperature and all the signal level considerations therein. However, with all of these topics that we'll cover today, I hope that by the end of this presentation, you'll understand that constructing your plan is key. Doing your best to understand your experiment, doing your best to select the proper hardware and deploy it appropriately, because these measurements are complex, and often with energetics, repeatability is limited. Even when we can repeat, we might not see the same phenomena in each and every test, and often these tests are somewhat terminal in the sense that you don't necessarily get the materials back. So each measurement possesses new and valuable information, and we hope to help you be able to collect that. So I'll add one more thing. All of these pictures that you'll see today in this PowerPoint, at least 95% of them, I have had a direct hand in collecting myself. So I won't go into too much detail talking about the specifics of most of these, but if any of it piques your interest, you can either put a question in the comment box or send us a message, and I'd be happy to talk to you about these collections, even share the data and the software with you so you can peer into it a little deeper on your own. So with that, we will look at our first topic, which is high-speed imaging for energetic events and why high speed is necessary. So I think this slide illustrates it pretty well. This is an energetics compound test. I believe it was TNT that was imaged here with a mid-wave camera at 800 hertz. And it is gone in a flash, as you see there at full speed. It's about 0.2 of a second for this entire event. But if we use that full 800 hertz, that high frame rate, and we slow down the image to 1/50th speed, we can start to see the shape of the plume and the dynamics, and also this rebounding effect. You can sort of see it wobble here after the blast. That's extremely interesting. Uh, and you need the speed to be able to see these high speed, high temporal dynamics of these energetics tests. You might even need higher speed. So, for example, if you were really interested in the initial expansion of this energetics test, you might even need higher speed, tens of thousands of hertz, which are the maximum frame rates that are typically acquirable with an IR camera. And so we do need to talk about that. So if you're familiar with high-end, high-speed visible spectrum systems, you might say, hey, that number seems a little low. And yes, while visible spectrum systems do reach higher frame rates, there is a good reason that IR cameras are limited to only kilohertz, tens of kilohertz. And that is because IR cameras must collect radiation directly from their target. There are not opportunities like there are with visible spectrum systems to use additional lighting or flashes or even heat lamps because the radiation emitted by our target is extremely important for our ability to calibrate that data because IR calibrations are based on precision black body measurements, comparisons to black body measurements. So we'll talk a little bit about that later. However, the main thing to consider is that when we run at high frame rates, when we run even at tens of thousands of hertz, we have to use shorter exposure times to be able to hit those frame rates. And what that means is that we have less time to collect signal from our target. So we typically need to worry about low signal levels more than high when we run at high frame rates. That's not always the case for energetic measurements. Sometimes we do have a lot of signal, a very hot or high temperature or high signal producing targets. But it is sort of the main limitation when we run at high speed. And detectors are often optimized to operate at the tens of thousands of hertz, especially on the high speed side. So there are some amount of detector limitations. These limitations can be addressed by different operating concepts, things like our HDR M700, which we'll get into, but still very powerful. So we need these tens of thousands of hertz. They are very effective even at those speeds for capturing the rapidly evolving phenomena of energetic tests. And without that speed, you run the risk of mischaracterizing these events or missing key dynamics, especially at lower frame rates. So teleops, as you covered, we have a couple of the fastest commercially available IR systems, if not the fastest, certainly the fastest in windowed operation. And those are specifically the teleops M3K system and the teleops M2K UD system. And on the next slide here, I have some specifications for those as well as a chart with some windowed frame rates. But one thing I want you to consider here while we're looking at high speed, before we start to look at dynamic range, is that all of the fast cameras, all of these high speed cameras are limited to a bracketed temperature calibration range, which means that they are only able to see as far as the calibration allows them to. There's a certain cut on and cut off point. Because they are geared for speed and they do require neutral density filters to be able to attenuate filter to reach higher temperatures as well as fluctuating frame rates. So keep that in mind. We'll talk about that a bit more in the high dynamic range section. We'll do a little comparison. But first, let's look at the specs of the fast cameras. So again, the fast M3K is a QVGA, a 320 by 256 pixel detector with 30 micron pixels that can do 3,100 frames per second in full frame at QVGA. And the M2K UD is a full VGA detector, a 640 by 512 with 25 micron pixels that can do up to 1,500 hertz in full frame. Both of those systems are midwave, midwave extended actually, which means they are 1.5 to 5.4 microns in spectral range. There's also an option to go to a midwave version, which is 3 microns to 5.4 microns. And they do have, as you'll see, wider pixels there. So that is part of the optimization that allows us to run at these higher frame rates with larger pixels. We can collect more signal and we alleviate some of those signal level concerns that we would face. So let's now take a look at the chart on the left here. These are windowed frame rates. So with all of teleops fast cameras, you can window them down or choose to give up pixels in your focal plane array to acquire higher frame rates, to acquire more speed. Mostly this is due to the data transfer, the amount that needs to be read and read off the camera in between frames. But you'll see there at something like 128 by 64, we can achieve 25,000 frames with the M3K. and 12,500 frames with the M2K UD. This is very effective. So we see a lot of folks, it might be scary to give up that amount of pixels, but you do have opportunities to regain spatial resolution with things like proper optics. Um, and it is extremely powerful and useful in energetics tests, which require that high speed to see these extremely high temporal dynamic events. So one example here that I'll just point out is the images on this slide are from a 120 millimeter cannon fire. And so this is the muzzle plume here that's coming out of the end of the barrel that would be off this way. And this is even the projectile that you might be able to see, depending on how blurry the feed is there. Uh, and this was captured at 1,000 hertz, so 1,000 frames per second. And you can see between each of these frames, 1, 2, and 3, the plume is expanded quite a bit. There probably are some dynamics there in its progression that we are missing due to this frame rate only being 1,000 hertz. We might want to look towards a higher frame rate, something on the order of maybe 10,000 hertz, in which case we would get 9 more images, 9 more sizes here as the plume expands in between each frame. And that would be pretty effective. One thing I did bother to map out is that the size of this plume, even in its largest here, would be about 200 by 200 pixels. And so if we look over to our chart with the M3K or M2K UD at this exact same spatial resolution we're looking at here, you'd be able to achieve almost 5 times the frame rate with the M3K, 5,000 frames. So you'd have 4 more images here to scrutinize this muzzle flash in between with a high-speed camera. And that can be absolutely necessary for these types of collections. So very important to consider fast cameras, but if you can deal with giving up some of that speed, or if you need to collect a wider range of temperatures than might be possible with a fast camera, we instead will need to look towards high dynamic range focus systems. And we'll do a quick comparison directly between fast cameras, mid-wave fast cameras, and the HDR first here. So if you remember, I mentioned those bracketed calibration ranges. This is sort of what we're talking about. So we need to use neutral density or OD filters in the fast cameras to be able to attenuate signal levels, to be able to unlock higher temperature calibrations. And so this is pretty characteristic. Filter wheel 1, negative 20 to 175. Filter wheel 2, 160 to 475. Filter wheel 3, 250 to 850C. But this isn't even the full story. So let's look at filter wheel 3. You might say 250C to 850C, 600 degrees. That's pretty good. But to achieve the upper and lower bounds of that calibration, you would need to vary your exposure time. So you need to use a shorter exposure time to reach the upper end of that range and a longer exposure time to hit the lower temperatures, which can be somewhat problematic. And certainly you wouldn't be able to image the entire range through one optical path with one exposure. Instead, if you needed to image a wider dynamic range, you'd have to look towards something like our all-new HDR M700 camera, which is able to view more than 900 degrees C in a single exposure and optical path due to a new on-chip saturation management function and a new digital ROIC. Excuse me a second. So that HDR is a vast improvement in terms of dynamic range over the previous generation fast cameras. And we will get into a bit of the specs on this camera and the operational concept today. But before that, let's look at previous approaches for increased dynamic range in infrared imaging, which you might be familiar with. And so these are things like multi-exposure techniques, things like super framing or EHDRI, as we like to call it at teleops, in which you can, with a fast camera, so we're back to the high-speed cameras, you can choose to give up some frame rate by collecting multiple data streams with varied exposure. So you could run a short exposure, a medium exposure, a long exposure, or some combination thereof. Whereas the shortest exposure time images would be able to see your hot objects, and the longer exposures would be able to see your cooler objects. And then you can go back and combine them in post-processing to combine into a single stream, which has a higher dynamic range than an individual exposure collection. And this is certain times great. But for energetic events, which are very temporal and have these rapid fluctuations, we can sometimes run into problems where in the post-processing we introduce temporal artifacts. And we also give up speed to do this. So we're lowering our speed and introducing artifacts that can be very problematic. So we don't necessarily recommend super framing or EHDRI for energetics tests. And I do have a good example of why that is the case on this very next slide. But before that, another attempt that you can make is with attenuation filters. So I did talk about how there's the different attenuation filters in the fast cameras. We do have certain models, such as our previous generation HDR IR family, which is now obsolete. They are not available anymore. They have been made obsolete and have been improved upon by the new M700 HDR, or Telep's multispectral family, which the multispectral cameras are still available. And the concept here in either case would be that we use multiple neutral density filters and a high-speed mechanism to rotate them into the optical path, either with a three-position mechanism or with a rotating filter wheel, which you can use to collect different signal levels and even combine them in post-processing, similar to what you would with a multi-exposure technique like EHDRI or super framing. And these are effective, but even with the multispectral camera, your maximum frame rates are on the order of 100 hertz per channel per 8 filters in our high-speed filter wheel, or 800 hertz total. And in post-processing, you do have to give up some of that to record a composite image. So they are useful in certain contexts, but instead we would recommend an HDR in this context. And let's take one more look at an example. So this is an EHDRI super framing example, and this is a battery research collection where there were two 18750, I believe, lithium-ion cells. So they are slightly larger than two AA batteries, and they were pushed to thermal runaway failure by thermocouple, at which point they ejected material and that material combusted. That's what you're seeing here in this frame. And so to image this, the hot gases as well as the low temperature background and the batteries itself, we had to run 3 different exposure times, one here at 5 microseconds, one at 25 microseconds, and one at 500 microseconds, where the lowest exposure time is able to see the peak temperatures in that combusting gas cloud, the ejection cloud, and the lowest exposures are able to see the edges of this hot gas cloud as they move back towards ambient temperatures, as well as the ambient temperature background, things like our tripod over here. And so when we combine these 3 data streams collected in sequence, one after another separately, into an EHDRI merged sequence, we do get this beautiful composite image, which is able to rectify the hot temperatures as well as the colder temperatures of the background. And it looks great, doesn't it? Well, let's look a little bit closer. I don't know if you can see this perfectly, but you see those 2 batteries right there in the frame itself. If you took that to be 2 batteries that have somehow broken apart during this collection, and you can see both of them, you would be misinterpreting your data. So what's actually happened here is the batteries were strapped together. They never broke apart. They were in parallel. But between the short exposure time, 5 microseconds, and the longer 500 microsecond exposure, those batteries have tumbled a bit. They have shifted almost 30 degrees in position, and that shift is recorded as a temporal artifact in our EHDRI merge sequence. So if you were to just look at that and say, wow, we can see both batteries and the entire plume, you would be misinterpreting your data due to those temporal artifacts. And that is a big concern with energetics tests, where there often are these often rapid, on the order of tens of microseconds changes. So this goes to show why we wouldn't necessarily recommend EHDRI or super framing approaches for energetics. Now, you could go back and look at each of these sequences individually and say, yes, I understand the true dynamics, as well as using this EHDRI merge sequence somewhat qualitatively, somewhat quantitatively, to say that, yes, it's great, we can combine the temperatures, but we do have to take it with a grain of salt, knowing that there are some amount of temporal artifacts that are obvious in there. So with that aside, let's understand that our new solution that improves upon this and moves us past the need for multi-exposure techniques is the Telops HDR M700, which is an all-new camera with a new 24-bit detector and a digital readout integrated circuit that's able to perform advanced on-chip saturation management functions. And the result of that is that we are now able to image more than 900 degrees C in dynamic range and snapshot dynamic range in a single broadband image with a single exposure, single optical path. And this is all complete with Telop's full radiometric calibration. In practice, we actually see ranges well beyond 1,000 degrees C, and I do have an example of that that's pretty impressive coming up. So I won't be going into too much detail on the operation of the HDR M700 in this PowerPoint. I do have one slide here coming up next on the operational concept, but it is a bit more complex than that. So if you do have any interest, we do have a lot more content available to you that you can go and seek out, or you can send us an email and we'd be happy to start a conversation and share that with you. We also have some new content coming out very soon. So if you're watching this at any point in the future, that's probably also available to you as well. But let's look at that operational concept before we look at some data. And again, the DROIC, or the digital readout integrated circuit, is really the power player here. And it is because it is able to fill and reset each of the pixels individually on the FPA of the HDR M700 up to 255 times per exposure. And what this means is typically where you'd be able to fill up a well and collect it till it's full. And if you exceed that, you have saturation. Instead, this detector can recognize that the well is starting to get full and subtract an amount of charge up to 255 times, and it can record the amount of times that it has subtracted that signal, such that a high temperature, a hot or a large signal producing scene constituent could refill the well a large number of times, perhaps hundreds of times, and a cooler object would not refill the well too many times, or maybe not even at all. And still in the end, we can rectify the amount of times that the well has been reset times the amount of charge that's been pulled from those wells, plus the residual value, to effectively image ourselves a much wider range of temperatures than was ever previously possible with a traditional FPA. And so again, I'm not going to go into too much detail here, but this is the sort of gears behind this powerful new technology. And instead, I want to show you what the result is. So this is it. This is an energetics test cleanup shot that was captured with the HDR M700 very recently. And as you can see there in the temperature profiles, the max temperature we're reading is well over 1,000 degrees C, and the range is also over 1,000 degrees C. So we're seeing those ultra hot temperatures over 1,000 C, as well as effectively ambient temperatures, or temperatures just above ambient, simultaneously with one camera, one optical path, no varied exposures. It is truly a first of its kind and very impressive data product that the HDR M700 is able to produce. This is a video of the same sequence, so you can see how the blast there occurs and the dynamics as it progresses. And the HDR M700 with the same exposure there of 204 microseconds is able to capture these very hot and the temperatures as they begin to cool off, as well as the full range, even during the moments of peak signal, which we find extremely impressive. And we do believe that this camera will be a powerhouse for energetics tests. This is a brand new system, so we don't have tons of examples yet. And some of the examples we have are obviously a little too secret to share online. But we encourage you to reach out to us if you do have a potential for high dynamic range needs. We'd love to talk to you, and we'd love to get started on optimizing your imaging plan in that sense. So now that we've talked about both high speed and high dynamic range, we need to mention calibration and emissivity. All of these cameras, high dynamic range, high speed, all Telop's cameras come with a Telop's proprietary global calibration, which is a black body free flux-based calibration, which requires no recalibration throughout the lifetime of the camera, and every operating space parameter available to that camera will provide you with a calibrated result in either radiometric temperature, in-band radiance, or in-band irradiance. And what this means is that it is the temperature that the camera would see if it were pointed at a fully emissive black body. And so what is emissivity? Emissivity is the ratio of radiation emitted by that target compared to a black body, which would be a perfect emitter, an emitter of 1, or a precision black body as we use in our calibration, which are 99.9 emissive for the most part. And the reason why we need to care about this is because energetic events have widely varied emissivity. It's almost never a true black body. Often these emissivities can be less than 20%, sometimes much less than 20%. And so this affects the validity of our radiometric temperature result. Essentially, in these cases where we have low emissivity, radiometric temperature will not equate to absolute temperature, as if the image did have high emissivity. So we need to at least qualify this, if not make an attempt to quantify our emissivity such that we can make a gray body approximation. There are potentials for error and limits there with the gray body approximation. Things like you might need to use multiple emissivities for different targets in your scene, or spectral emissivity could be a concern. Emissivity might not be consistent across the full bandpass of the camera. However, the more important part is understanding the difference here between radiometric temperature and in-band radiance compared to absolute temperature or absolute radiance. So if you can characterize your emissivity, we often ask how well can you characterize your emissivity. We do have tools for that available to you directly in teleops software, and that's what you see here in the data on the right. So I've applied an estimate 15% emissivity correction to this sequence of this energetics test, and you'll see there that the range increases in absolute temperature with this emissivity correction applied to over 3,000 degrees C as a peak temperature that we're viewing there. Would this apply to more than the hot gas cloud? Not likely. We might need to apply a separate emissivity correction if we were trying to image, let's say, the walls of the bunker here. But this is all sorts of things we need to unpack and understand when we start to look at our imaging plan and our eventual data goals. So with those three topics briefly touched on, and I know it was brief, if any of that has piqued your interest, please do start a larger conversation with us. But I hope that it starts to have you understand that when we're trying to employ best practices for energetics collections, no single scheme or device is going to be optimal for every test. We need to try and optimize for what we expect to see, for what we expect from our tests, what we know about our tests. And while complete knowledge is not always available, due diligence and good preparation will always improve your data quality and should always be employed when trying to make your imaging plan. And we would love to help you with that. So we have done hundreds of energetics collections, and we've done a lot of trials, and with those trials sometimes come errors. And we have learned from all of those, and we would like to help you learn and to help you have less hurdles to clear when setting up your imaging plan. Common topics that we talk about with all of our customers that we'd love to help you with are things like speed and dynamic range, which we've talked about today, but also considerations like optics and spatial resolution. We didn't touch on optics nearly at all. However, when we start to talk about spatial resolution and giving up pixels for the FPA, teleops does have a full suite of optics that can help ease that pain. Past that, things like safety and triggering. We do know how to protect our cameras. Protecting the operator is normally on you guys. However, triggering. Our cameras can accept TTL triggers, and they can also do conditional triggering based on scene, which is sometimes interesting or beneficial to energetics collections. So past that, we can also talk to you about emissivity. This is verging on a complex topic. This is not necessarily an introductory topic, but if you'd like to talk to us about our calibration and emissivity and the effects thereof, we would be more than happy to share with you what we've learned as well. So to wrap up, or to begin to wrap up, we know that energetics collections are inherently unpredictable. And so this planning, this optimizing, choosing the right hardware, deploying it appropriately, understanding our results are all important for the validity of our results, which we do want to be high quality in the end. So what are your collection goals? We would love to help is the message that I'd like you to take away from this presentation here today. And to conclude, obviously, we've talked about having the proper equipment. We've talked about fast IR cameras. We've talked about high dynamic range systems. And we've also talked about emissivity and calibration. But there are several other topics. So if you would, I encourage you to jot down our email here. This is now our field application group email, which I am a part of, fae@teleops.com. If you would like to reach out and start a conversation about your needs for an IR imaging plan for an energetics test, we would love to be a part of that, and we would love to help you collect some great data. So that is what I have today. Thank you for joining us. I will now look towards the question box. If you have any questions based on this webinar, please do write them in right now, or again, you can email them to us at a later date if you're watching the recording after the fact. Let me look towards questions and see if any have come in. Okay, we do have one. It is asking, what is the spectral range of the HDR M700? That is a 3 to 5.4 micron camera. It is a mid-wave camera at the moment. However, we are looking towards developing a long-wave version of an HDR system, as well as we are talking with some customers about potentially introducing a mid-wave extended version. However, there are some limitations there. Once you go to a wider bandpass mid-wave extended, you might not receive the same high dynamic range performance. So we're still testing the feasibility of those systems, but those might be new products in the future for teleops. That would be a long wave or a mid-wave extended version camera. But right now, it is just a 3 to 5.4 micron mid-wave camera, that HDR M700. Okay. I think that is it for our live questions today. So with that, I will move to close. Thank you for joining us today for this teleops webinar. We appreciate you being here, and we encourage you again to reach out and start a conversation with us. We thank you for your time, and we hope to see you at the next one.